Morning class. Today we've got to move on, going over some 2D momentum. I don't have my graphics tablet, so I'm going to have to use a previously already filled in version of today's notes. So please follow me. I'll try to point at things with my mouse as best as possible. So let's see what's going on. So the goal is we are doing with two-dimensional vectors, right? We've been working this, doing things with components or making triangles or whatever have you, and we should be able to apply this two-dimensional math to all the things that we did in Physics 11, be it just regular old motion, what we call kinematics, or to forces. Energy is a scalar, so we don't need to worry about that, but momentum is also one of those things. Now, I understand that some people might not have covered momentum because there wasn't enough time in their grade 11 class, and that's okay. Momentum is pretty quick, and it actually follows along pretty easily. So let's go ahead and introduce what the concept of momentum is, and then we will go from there. So Newton, he described momentum as a quantity, or how much motion there is. It's dependent on both mass and velocity. So if we consider the momentum, we use the symbol p, a lowercase p, to represent momentum. Momentum will be equal to the product of mass and velocity. Both momentum and velocity being vectors, they're going to share the same directions. We're just going to remind ourselves momentum is a vector, so it means the direction is going to be pretty important. Now, which of these two situations would have more momentum? A 90-kilogram football player, supposed to say, not playing, running at 3.5 meters per second, or a 55-kilogram jockey running at 3.5 meters per second. And in this case, they have the exact same velocity. They're running equally fast, but since there is more of the football player, that means they have more momentum because there's more motion in total because there's more mass going in there. So that'd be right. Now, this little follow-up question here, how could the jockey gain more momentum than the football player? Well, to do that, can a jockey who is smaller ever have more momentum than a football player? The answer is yes. They just have to have more motion, which means if they can't have more mass, they have to compensate by having more velocity. So since the football player's not quite double the mass of the jockey, if the jockey ends up going double the velocity of the football player, they'll have more momentum at this case. So the jockey could go faster, and I did a little like P is equal to M times V calculations to find out the total momentum of the football player. And then I used the mass of the jockey to see what would be the threshold velocity. So the threshold velocity would be 5.73 meters per second squared. That's the momentum. So that's the concept of momentum. That's what it is. It's how much motion is there, and it's easily calculable by taking the mass and the velocity. Now we also have a term. A term is called impulse, and this impulse is the change in momentum. Remember, change we represent with delta. Change in momentum is equal to the mass multiplied by the change in velocity. In red here, I have mass times change in change in momentum is equal to change in mass times velocity. While it is theoretically possible for something to be moving at a constant velocity and its mass to change, that's not usual. Usually when something's moving, its mass is relatively constant and it's the velocity that's changing. And so that's why this one's in red. It's not really that common. What's going to happen most often is your change in momentum will be a constant uniform mass multiplied by change of velocity. Now, where I go from this is I know that change in velocity relates to acceleration because the change in velocity divided by time is acceleration. So I can actually replace change in velocity by acceleration multiplied by time. And this allows me to take a new look because I know mass times acceleration is net force. So just by relating our change in velocity to acceleration, I've created a secondary way for us to calculate the impulse. The impulse is the net force multiplied by the amount of time. And hopefully this makes sense because impulse is the change in momentum. It's the change in how much this thing is moving. And what do forces do? forces provide accelerations. They change velocity. So the net force multiplied by the time is just saying, I'm applying acceleration on a mass for this period of time, this much time. I'm going to change its velocity for this much time. That will get me its impulse. That'll give me its change in momentum. So we have our relationships here on this. Now, since our momentum relies on mass velocity, and in most situations the velocity is more likely part to change, you can simply equate these relationships. The change of momentum is equal to mass times change of velocity, which is equal to the net force times time. And you would, sorry, that's what's supposed to go in this this box here. I just wrote it in the wrong place, so that's fine. What's going on here is this requires some net forces, which are outside forces acting on the system. This impulse formula is all about open systems with outside forces. So that's what's going on here, is we can calculate change in momentum. Now if you're wondering, like, well, Mr. Westergaard, could I not just use my regular forces to find acceleration and then find regular kinematics to find velocities, for example? And the answer is yes. Yes, you absolutely can. This is just a relationship that explicitly connects the kinematics and forces together, but right, don't feel like you have to use this specific relation to do it. This is just, when we look at momentum, there is a relation this way. Now, where momentum is truly useful, this is one. So if you're going to fall asleep at any time, not now, that this is what it's really important, is the law of conservation of momentum. The law of conservation of momentum is saying that the momentum within a closed system is constant. That means if you have a closed system, no outside forces, the momentum will not change at all whatsoever. The momentum in a closed system is always conserved. This means for any collision or explosion or events that happen, the total momentum before the collision should be the same as the total momentum after the collision. So for example, here's our little diagram. If I have a ball and it's flying at a box, so that's what I have here in black, just a ball flying at a box. And then the ball were to strike this box and they are to stick together, the momentum of the ball and the box separately should be equal to the momentum of the ball and the box together. Now, if you might say, like, Mr. Westergaard, when I hit a ball with a box, that'll make the box slide, but the box slides because of friction. And you're like, fair enough. What we would use is we'd use our law of conservation of momentum to consider the instant of the collision. That allows us to find the velocity that it begins to slide across with. So it's just, so the law of conservation of momentum, you can time limit how close your system is, and you can say, like, okay, I want to know just before they collide and just after they collide, and that'll be a useful tool for us. We'll look at some examples of that. I think I put one on this sheet. Yeah, that's kind of the premise here. So this is our law of conservation of momentum. This is an important thing. Momentum within a closed system is constant. It's not going to change. Now we have two categories of collisions. There's things that are called perfectly elastic collisions. These are perfectly bouncy ones. These are collisions where the momentum and kinetic energy are both conserved. And then there are inelastic collisions, which tend to be stickier collisions. These are where momentum is conserved, but the kinetic energy is not. Now you might be thinking, Mr. Westergaard, I know you talked about the law of conservation of momentum, so momentum is conserved, that's fine, but isn't there such a thing as the law of conservation of energy? And you're right, there is a law of conservation of energy. But just because energy is conserved doesn't mean that that energy needs to stay as kinetic energy. If I were to think of, here we go, I have this situation, a car is rear-ended by a bus. They're both moving, so they both have velocity. When they collide, if I were just to imagine a car being hit by a bus, it would make an enormous quantity of noise. There would be a lot of deformation on the car itself. The car would be like crushed a fair bit, and all these things. And noise and the deformation of the car and all these are forms of energy. So that the kinetic energy will be turned into. So that's what's going on here, is the kinetic energy is not conserved, but the total energy, including things like noise, like deformation of objects, and all these sorts of things, that's conserved. So in elastic collisions, the momentum is conserved and the total energy is conserved, but not kinetic energy alone. The majority of collisions are a bit about, honestly, the majority of collisions, almost all collisions are inelastic collisions. There's almost no such thing as a perfectly elastic collision because that requires no non-conservative forces. And as we've learned, non-conservative forces are kind of everywhere. I'd say the best example of perfectly elastic collisions would be particle-to-particle collisions. This would be a case where I have like a proton bouncing into another proton. Stuff like that. So let's go ahead and do an example to kind of get us used to the law of conservation of momentum. So I've got a car coasting on 3 meters per second. So here we go. I've drawn my car going 3 meters per second. And it's rear-ended by a bus going 12.5 meters. So here's my bus coming into its rear at 12.5 meters per second. Now this is before they've actually collided. But after the collision, so I'm going to draw my after over on the other side, the car is now going 15 meters per second. And the question asks, how fast is the bus going? Well, the law of conservation of momentum states that the total momentum before the collision should equal the total momentum after the collision because, as we were saying, the momentum in a closed system is constant. The system, I'm just going to say, is the bus and the car together. So the momentum of the bus and car together should never change. So what happens before should equal what happens after, so long as those are the two objects in my system. So we're going to do this by finding the momentum of the bus to start and the momentum of the car to start. So mass times velocity and mass times velocity. And that should equal the momentum of the bus after, mass times unknown velocity, and the momentum of the car, mass times final velocity. And then I do some calculator work and a little bit of algebra, and we should be able to find the final velocity of the bus. Now, I went through that very quickly. Feel free to pause and double check all the numbers and the math. That's fine. But frankly, this problem itself is actually too simple. This is what we would have done in physics 11. This is just in one dimension. This is just forwards, right? And if this is just forwards, that's 1D. That's not where we're going. Remember, our goal is to do things in 2D, in 2 dimensions. So this is just to introduce our idea of the law of conservation of momentum. We're going to be moving on and doing a little bit more. So let's take a look. What's going on with 2D collisions? Momentum's a vector. We use regular style vector addition to find the total momentum of a system. So it just means do the same thing, but now we have to think about x components and y components. That's it. So here's an example. I'm sitting in a chair and my head explodes into 3 pieces because that's how it feels right now. My head is normally 2 kilograms and a 0.75 kilogram piece is going to launch straight upward. A second piece is launching to the right, that's 0.5 kilos, and what would be the velocity of my third piece? So here we go, I've got 1, 2, 3 pieces, top, bottom, and object C. I don't know why I call it T, B, and C. I don't know, I just did it. This is what my head looks like post-explosion. And I know that the momentum of this system after the explosion, because the only thing I'm looking at my head, should look like the momentum of the system before the collision, before the explosion. So here's my head before the explosion. Now, I'm sitting in a chair. How fast am I going? I'm not. So my momentum would be my 2 kilograms multiplied by 0, or 0x component, 0y component. That's my initial momentum. 0x component, 0y component. Looking at the top part, what do I see here is going straight upward, so it should have 0x component, and its momentum would be mass times velocity. So there's mass times velocity, and it's all y component. So you get to put that in. And part C here is going into the right, so it has 0.5 times 1.4, that's its x component, but it has no y component, so that's why I put in 0 for its y component. In part B, I have no idea what its velocity is. So I'm going to do mass times velocity, 0.75, because that's the remainder, right? 2 kilograms, 0.75, 0.75, and 5, that should add together. 0.75 times velocity x, 0.75 times 5 times velocity y. And now, since everything is nice and organized in vector notation, I can just do my top. 0 is equal to 0 plus 0.5 times 1.4 plus 0.75 times vx. And then on the y, 0 is equal to 0.75 times 3.1 plus 0 plus 0.75 vy. Going through, doing the math, we get Vx is negative 0.9. So negative 0.9, I suppose I called to the right positive, so that means this negative is to the left. And Vy is negative 3.1, and I called up positive, so it means down is negative is down. And so I'm just going to take these values, construct my triangle, use my Pythagorean theorem, use a tangent to find the angle. And so here we see it's the law of conservation of momentum. The momentum before the event, in this case the explosion, should be the same as the total momentum after the event, the explosion. And the only thing that I did different from this example compared to this example with the bus and car is that I split things into their x and y components. And by splitting things into x, y, y components, I am now taking into account the two-dimensional nature of this problem. Hopefully this is making sense to us. If you need to take a moment to pause and catch up with things, of course, do that. Let's take a look at the next problem now. Okay, so just a little reminder, vector addition can be done with components or can be done with trig. Remember, trig, you only have to have 3 vectors. So let's take a look at the situation. We have 2 cars, and they had a collision at a 4-way stop. Car A was traveling east, so here's A, and it's traveling east, and car B was traveling north. There we go. So this is what that looks like before the collision. And then after the collisions, they stick together, and then they slide 23 meters at that angle, and there's this much friction. Now, this much friction before the car stopped. Now, who should get a ticket? This problem is a little bit more tricky, but looking at it before and after, I know that the momentum before the situation should equal my momentum after the situation, after the collision. So if I say, well, what is my momentum before? It's momentum from A and momentum of B. And what is my momentum after? It is just the total. Now I know what's going on here. Everybody ignore that velocity at the moment. We don't know what that is yet. As I know that it's heading at an angle 35.6 degrees north of east. And these are going north and east specifically. I've specified my directions in terms of north and east. I should probably stick with those specified directions. And that's actually going to be really good for us because A is all x direction or east, and B is all y direction, all north. So I'm going to stick with north, south, east, and west as my axes, even though after my collision the acceleration isn't there because I've defined my axes in my problem by talking about the specific directions. Okay, let's talk about what's happening after. There's friction bringing this object to a stop. So if I think about it, what forces are acting on these after they're stuck together? But when they collide, they're not going to be stomping on the gas anymore. So the only force that's going to happen is friction slowing them down. So I could use my net force is equal to my quantity of friction to find the acceleration of these objects, of them being stuck together. And when I know the acceleration of these pieces stuck together, and the fact that it comes to a stop, and that it goes 23 meters, I could use my kinematics relations to find out what is the velocity that they started sliding together with. Now that I have the velocity of them sliding together, I can relate it in this relationship here. Now, I've actually, on one side, I've done it as a trigonometric thing, and on the other side, I've done it as a, or sorry, never mind. I'm doing this in components the whole way. apologies. So everyone, I found the velocity is 23.9 meters per second in this direction of 23 meters. Now, looking at this, this is a momentum relationship. I need to know how these momenta fit together. So this is my momentum total, momentum stuck together, momentum together, right? The mass of them together, so I added the masses, 1150, they're both the same mass, and I'm multiplying it by that velocity. That's the direction it's going, 35.6 degrees north of east. Thinking about this, specifically, A is the only one that provided x component, so the momentum of A will be the x component of this vector, and B is the only one that's providing y component, so the momentum of B would be the y component, because the addition of A and B should equal the total momentum. And so I got it, mass A velocity A is equal to 1150, that's the mass times velocity A, which we don't know, and mass B velocity is 1150 times velocity B. Looking at this, I can use just regular old sine and cosine. I see that the y component is opposite, so that would be sine. So I use the 2300 times 23.9 times sine 35.6, and that will allow me to solve for velocity B. Velocity B is 27.8 meters per second. And here, since A is the x component, I notice that it is the adjacent side, so I'm going to use my hypotenuse, 2300 times 23.9, and I'll multiply by the cosine of 35.6. If I divide out the 1150, I found a velocity A is 38.9 meters per second. So you can see I've taken this PA, this momentum A, and this PB, momentum B, and they should add tip to tail to equal momentum total, which is what stretches across them. So this way I used kind of a trigonometric way to visualize it, but then I just broke it down into my components like so. In this case, the answer is who should get a ticket. Looking at both of these, this is a four-way stop. 27.8 meters per second is close to 100 kilometers per hour. Anybody coming into a four-way stop at 100 kilometers per hour should get a ticket. And this person's going about 120, 130 kilometers per hour. Again, both of these people are maniacs, and they probably killed themselves, making the whole world a whole lot safer for everyone else. So, yay. But yeah, they both do bad, because don't come into four-way stops fast. You should be stopped at a four-way stop, not 100 kilometers an hour. Anyway, just finally answering that question there. Hopefully this made some sense to you. I hope I will be back and not super ill tomorrow. Best of luck with 2D vectors and momentum.